Dr. Michael Wolfin is an assistant research professor at Penn State University. Michael will give us a presentation on the use of essential oil products and natural attract and kill stations to control mushroom fly populations. As we're all aware, flies are one of the main causes of mushroom disease infection and spreading, so it will be interesting to hear how this problem is being addressed in his research. Michael, I'll hand over to you at this stage.
Sure, thanks. Can you hear me?
Yeah, perfect, Michael.
Great. Yeah, thanks for that introduction. I also think John did a great job introducing the mushroom industry in Pennsylvania, as well as what we do here at Penn State. I'm in the entomology department. I'm an entomologist. I'm an insect behaviorist, and I specialize on pests of mushrooms, specifically fly pests of mushrooms. And one thing that that I think might be unique to Pennsylvania, as John pointed out, is that we have a very, very concentrated number of farms spanning a small unit area. But with that comes that pests of mushroom farms are not just pests of mushroom farms, because they are directly next to residential areas. So a mushroom farm will be less than 100 yards. 100 meters, sorry, from a mushroom farm will be less than 100 meters from a residential area. And all of these pins represent an individual neighborhood that is being invaded by mushroom flies. And in the fall, that's when peak mushroom fly season is. It's not uncommon for a person's home to have tens of thousands of mushroom flies in it as a result of spillover from mushroom farms. So this is a major, major problem here in Pennsylvania. Over an area of 242 square miles, there's over 175 neighborhoods reporting invasions. And these invasions are really, really severe. We're talking tens of thousands of flies entering people's homes on a daily basis. That's every day for a couple of months. So it's a big deal, in addition to the mushroom yield and quality concerns, but specifically there's a residential component as well. So I'm looking to introduce new technologies on killing these mushroom flies. I'm looking to bring attract and kill stations into the mushroom industry. Very quickly, an attract and kill station is, let's say you have a crop, any crop, it doesn't matter what crop it is. This crop has a pest infestation. What we do is we use a strong attractant to really create a billboard, to find something that's really, really attractive to the pests, even more attractive than the crop. This is possible. Let's just say that these flies are attracted to red circles. These red circles are treated with a strong insecticide, and the fly populations, when they are attracted to these red circles here, they touch the red circles, they get dosed with the strong insecticide, and then they die. And that's the main overview of how an attract and kill station works. I want to bring this technology to mushroom farming, and I'll just say it up front. We've already figured out the strong attractant. We've already figured out the strong insecticide, and now let me show you some data. So let's talk about how we found the strong insecticide first. The first thing we did was discover this electrostatic screening. This electrostatic screening is really important because it's an excellent delivery system for powdered insecticides. If you think about it like you rub your hair on a balloon, the balloon will stick to your hair. That's sort of how powdered insecticides stick to the screens. We tested a number of different powdered insecticides. I'll highlight this one. I'll draw your attention here to Ecovia WD. Ecovia WD is fee for 25B exempt in the United States, meaning that it's the lowest risk insecticide, and it's immediately approved for on-farm use. So we didn't need to get any registration for this product. We could test it on farms immediately because it's such a low risk. So let me show you the first on-farm studies in 2020. The only thing we did here was, so here's our first attract and kill station. This is what the attract and kill station looked like after 2 weeks. And all of this black material here, those are flies. Those are dead flies that accumulated on the bottom of our attract and kill station. And then if we look down below the attract and kill station over here, you can see that there's even more dead flies. These are mounds and mounds and mounds of dead flies, all accumulated in a 2-week period in September or October. And here's what the data looked like. So during the first 2 weeks of the study, under one attract and kill station in one growing room, we collected about 935,000 dead flies. I collected these flies just from the attract and kill station itself, not from below it. So I didn't sweep up any of the dead flies from below it, just the attract and kill station. I came back 2 weeks later, and these are first break. These are hung in first break. This data were collected during first break. Came back 2 weeks later, and there were about 660,000 dead flies, which was really good. But then because of COVID, I couldn't get back to the farm until December, and there were only 27 dead flies across 3 attract and kill stations, or an average of 27 dead flies across 3 attract and kill stations. This is not because the winter killed them. We had a very warm November. This was because there were no more flies on the farm. We completely eliminated all of the flies on this farm through the use of these attract and kill stations. It took about 50 days. The grower reports from this first from when they first placed the attract and kill stations on the farm, and you'll see why that around 50-day number makes sense. So then we've continued this study through 2021. So we've got 2 years of on-farm studies. And I just want to point out that this is the peak time. This is when the mushroom flies should be at their maximum numbers. I haven't collected all of the data yet from 2021, so this is just early data from April through August. August is when peak begins to set in. On the y-axis here is the mean number of phorids killed per room per week, and on the x-axis here is the week. And we're just looking at the number of phorids that were caught on the fly monitors. So we're trying to see if we're reducing we're trying to see how we reduce the population over time, essentially, on these Pennsylvania fly monitors, because these monitors are up all the time. The black lines indicate the farms that are using our attract and kill technologies, and the red lines will indicate the farms that are not using our technologies. And you can see that there is a stark difference, at least early in the season here, between the farms that aren't using our technologies and the farms that are. As the pest numbers are not very high, they're basically non-existent for the farms using our attract and kill technologies. And then even as it starts to ramp up, they remain low. I'm still collecting and analyzing data from September through December, but I expect it to go up, and I expect it to go up significantly, but not reach the peaks that we're even seeing here on the farms not using the attract and kill technology. Here's an easier way to look at it, where we just averaged all of the growing rooms that are not using our technology and that are using our technology. You can see that there's a stark difference between the number of phorids in one room per day. So this is a 1 room and per day number here that we're looking at. So let's talk about the mushroom growing cycle, which I know you're intimately familiar with, but maybe how you don't think about it is that it's also the mushroom phorid growing cycle or I know that C. arids are a major problem there too, and the C. arid cycle is pretty similar. There are some differences, but it's pretty similar. And that during spawn run, the insects enter the growing room, and one female can lay 50 eggs here. So if you start with, let's say, 3 females, 3 females lay 150 eggs, and that's what 150 eggs just looks like representatively. So from these 3 females, you can already see how the number balloons from 3 to 150. As spawn run continues, the eggs hatch and develop, and they eat the actively grown mycelia in the compost. They develop further during case hold, and then eventually they pupate. They form pupae, just like butterflies and moths do, and they remain that way for a couple weeks. And then during first break, as you're all familiar with, that's when the populations begin to explode, right? And you see all of these big, beautiful flies emerge from your compost, and then they leave the growing rooms, And then what we've noticed here is that these flies are crepuscular, which means they're most active during dawn and dusk. So they actually form mating swarms around dawn and dusk, maybe an hour and a half before sundown, an hour and a half, or an hour and a half before sundown, and an hour and a half after sunrise. So it doesn't mean they're not mating all of the time. I'm sure they are, but they form these clumps, these mating swarms here on top of the growing rooms. Eventually, both the males and the females will make their way into spawn run rooms, along with flies from other farms, because they're so concentrated here. They enter the growing rooms, and then the process starts all over again. But now, instead of just 3 insects laying 50 eggs each, or 3 females laying 50 eggs each, we have 75 females laying 50 eggs each, and you can see how it can just balloon out of proportion from there, just achieve these astronomical numbers of flies. So the questions that I want them to answer is, what can we do to stop the flies from entering the growing rooms to lay their eggs in the compost? And essentially what I'm asking is, I want to understand how the flies locate the compost. Conversely, I also want to know what we can do to stop the flies from exiting the growing rooms to mate. And again, what I'd like to understand is, I'd like to understand how they locate the outside. It sounds like a really obvious question, and honestly it is, but as an insect behaviorist, I need to get into the brain of what an insect does and how it uses its senses. It has different senses than we do to decode the physical world around them. They're not very good at vision. However, they are good at detecting light, which is a different skill. They're very, very good at following odors, and they follow their nose. So I really wanted to understand, it's not really how they locate the compost, it's actually how they enter the growing rooms. And just spending a couple years on the mushroom farms, there's just a zillion different ways that the flies can enter the growing rooms, whether it's portable air conditioning units, whether it's through attics, whether it's just poorly maintained buildings, or whatever this patch is. There's different necessary piping into the rooms and out of the rooms, but also the doors have to be open, and you can keep the doors shut as best you can, but there are times where the doors have to be open. The flies can enter very quickly, during casing, to water, to do temperature checks, and it just seems to me that there are lots of different potential ports of entry for the growing rooms, and once inside, they lay their eggs very quickly. These insects only live about 4 to 5 days as adults. So as soon as they get into a growing room where they can lay their eggs, they're going to lay their eggs fast. So I think it doesn't matter I think it's a low problem. I think it's not as fruitful if we kill the flies during this stage, because if we kill that fly, we don't know if it's already done its damage. And if it's already done its damage, if it's already mated or it's already laid its eggs, it doesn't matter if we kill that fly was dead already and it's already hurt our crop. So I wanted to focus on how the phorid flies locate the outside. And this is the same thing for Sierrids. We know that light is important. Okay, we use these traps, they're attracted to them, but we also know that sunlight is very important, because they are crepuscular, and they time their behaviors based on the amount of sunlight and the intensity of the sunlight that they make their mating swarms. And the only source of sunlight in growing rooms are these vent windows here, that in the US, they're either covered with a green filter, an orange filter, or a blue filter, and those let in various amounts of sunlight depending on the color. And what I want to do is I want to crank this up. This is what I want to focus my attract and kill station on. This is the attract. I want to create a billboard using these windows. And that's essentially what we did, was we turned these windows here into a very, very strong, attractive signal here, where when the flies first emerge from the compost, they are looking for that sunlight. They need to find that sunlight to go outside to mate and lay eggs. And if we give them a very obvious source of sunlight, a billboard that said, hey, outside is over here, they're going to be very strongly attracted to it. So what we did was we replaced the orange filters over the vent windows with the electrostatic screening that I talked about earlier. The electrostatic screening was treated with the Ecovia WD, like we talked about. This is very good because this screening lets the mushroom odor out, and the flies are still attracted to it. They will try to enter the room through this electrostatic screening. They can't walk through the screening, and they get dosed with insecticide. So these flies perish, these flies die. And we don't know how to quantify, we don't know how to measure how many flies are killed on the outside. However, on the inside, when these vent windows are covered with the screens, the flies leave the growing beds, and they actually leave the growing beds much faster than they would. For the growers, they feel like they have more flies because of this, but actually the flies are leaving the growing beds and going to the windows just more rapidly. And this just happens over and over and over again, where the flies emerge from the growing beds, go to the windows, and then just die. We found that it takes about a minute of exposure time to the one of these attract and kill stations to kill a fly. A minute of exposure time is not a lot of time, especially for a phorid. It's a longer time for a Sierrid because the Sierrids like to fly. There's different behavioral, there's different behaviors at play here. But essentially what we're doing, and the reason this 50 days is important, is because we're killing the next generation of flies. And what I mean by that is, let's say we're starting over again and you've installed your electrostatic screens now with the pesticides. Well, let's say you just have fewer insects because many of them tried to enter through this screen and they couldn't because they were killed. However, some of them still get in because the doors are open, because there's many different ways to get in. Even though this is the most obvious way and the fly will take the most obvious way, some of them don't. A female comes in, but instead of laying her 150 eggs, she only lays 50 eggs because she's one female. We cannot kill these eggs or the larvae, so they hatch and develop in the compost as normal, just like they did previously, through case hold, they pupate, and then they emerge just like normal. However, after they emerge, they see this, they see the attract and kill station, they see the strong sunlight, and they try to exit as fast as they can through the attract and kill station because they see the billboard that's treated with a strong pesticide. And this is the result. This is what it looks like after 2 weeks of first break. And I know I showed a video earlier, but these are all dead flies here. This is the 935,000 dead flies that I actually counted by weight. I didn't count them all out. And what this did was the flies never made it out of the growing room. So the next round of flies never really made it to the next spawn run rooms. So I had the growers telling me, we're using these products, but it's not killing any flies. And that's because we couldn't stop the flies that were emerging from the compost. Those flies were emerging from the compost as normal. However, after a cycle or two, the flies stopped emerging from the compost because they didn't lay any eggs. And that's when the growers reported that there were no more flies. And that's when the control happens. When you've killed all of the flies that have emerged from your compost already, there's no more to lay eggs and there's no more to emerge again. So it's slow. It does take a cycle or two to kill all of the flies, but we've shown that on a couple of different farms now that it does work, as long as there aren't too many flies coming from neighboring farms. That can complicate things. And I implore the growers to talk to their neighbors, and because that's where their flies are coming from at this point. Let's talk very quickly about lofts. Not all mushroom farms in Pennsylvania have lofts, some of them do, but the lofts can very easily be accessed by mushroom phorid flies, as well as Sierrids. And flies can use these lofts to travel between the growing rooms without going outside. That's why not all of the flies are killed during winter, because some of them are able to stay alive and travel between rooms easily through the attic. And it's also a good place because the flies don't know that the mushrooms are in the growing rooms. So if they're following their nose to where the odor is, they may believe, or they may follow their nose directly into the lofts and try for a long time to find the mushrooms that are in the lofts, even though they're not in the lofts. They're in the rooms themselves. So I think this is another billboard. It's using another sense and another behavior that these insects need to follow to find mushrooms. So I think the lofts can be used as another attract and kill station. So the growers go upstairs and the growers go to these lofts and they apply the pesticides in the lofts, which is fine because there's no crops up there. They can broadcast the pesticides up there because there are no crops. They just use a hand duster like this, and they achieved some really good control. Some of the common mistakes are starting too late. These methods require a full cycle everywhere on the farm to protect the crop. So starting when you have lots of flies is too late because you're going to have the flies for another 50 days or so, depending on how many mushroom growing rooms you have. The other thing I've seen is that the growers cover the electrostatic screening with plastic, with dark plastic. And if no light gets in, you're going to have no attract and kill. It's just not going to kill anything. And finally, installing the screen over the orange filter. And I just want to show a picture of that, where I took this picture when the grower told me it wasn't working. The flies were not attracted to the light. And I had him go outside, rip off the orange screen, and then I took a picture again. Within 5 minutes, the screen was covered with flies, and you can see the pesticide here. The flies are about to drop and die, and pretty soon there was a mound below the screen, and this is where that picture came from. So very quickly, a couple current and future projects. We're continuing to monitor the populations for the full season. We're calculating return on investments using these methods, and we're assessing new pesticides, not just the Ecovia, for use and control and management solutions to mitigate resistance, as well as always looking for new locations for my attract and kill stations. And we're doing specifically this right now. We're doing more tests with Sierra flies. I don't know if I have time to go through the summary, but the electrostatic screening is an effective delivery system for the powdered insecticides. Ecovia was a really good really effective pesticide, and the insects only needed to be exposed to it for 1 minute. The farms that didn't use our methods had a lot more flies than the farms that did, and the lofts are also important for attract and kill stations. With that, I want to thank all of my funding agencies, the Pennsylvania Department of Agriculture, as well as the U.S. Department of Agriculture and Georgia Mushroom Company, and everybody who's helped on the mushroom fly team along the way, specifically Hector Martinez, and Shiraki Mushrooms, who allowed me to do a lot of work on their farm, and they did the lion's share of the work. So with that, I will pause for questions. How did I do on time?
Not too bad, Michael. Not too bad. Well done, and very interesting. Just the first couple of slides, I think, was shocking. The amount of flies that was killed on the what should you call it, electrostatic screens. Yeah, so it's crazy. So just first question coming in: how often do you have to change the electrostatic screens?
That's an excellent question that I should have mentioned in this talk. So the electrostatic screening is expensive. It's about, I want to say, and I think in feet too, so we're going to have to convert this. It's about 36 inches by 100 feet. It's about $200. However, you don't have to replace it at all. My growers have not replaced their electrostatic screens since they started working it in 2020. And part of the reason is because they actually create a frame for it, so that if they need to take the screens out for whatever reason, they can just remove this wooden frame here. And that adds to the longevity of the screens as well. So I've had one grower who has fans over, fans like in front of the electrostatic screens here, and those fans are on and off constantly, and the screens are in perfect working condition. So as far as I know, almost 2 years into the studies, they don't have to be replaced. They're really hardy.
Okay. Perfect. So second question here, are Sierra Sierra flies equally attracted to the billboards?
The behaviors are different. While the easy answer is yes, they are equally attracted to the billboards. Phorid flies tend to land on something and then walk around it to investigate. Whereas a Sierrid fly will fly over to it, land, and if they don't like it, they will hover around it before landing again. So while the answer is yes, they are equally attracted, they're probably less likely to spend a full minute at once to get dosed. However, a strong attractant like the sun can create what we call a super stimulus or a behavioral trap, meaning that the fly will fly over, land on it, assess it, realize it can't get through, and then fly away. However, after it's flown away, it will take another visual assessment of the room and go, oh, wow, that window over there looks like the sun, and it'll fly back over and repeat the process. That may not be necessary for phorids because they will land and walk around for a minute and then die. Sierrids might have to repeat the process a couple times, but that does happen. These flies don't have very strong memories. They will, after they fly away for a little while, they'll just go right back to it.
Okay, perfect. What I'm just taking away from that as well is the actual physical integrity of tunnels. Here, sorry, Michael, in Ireland we use tunnels rather than the concrete structure. So the actual physical integrity of tunnels is such an important to actually prevent the flies from getting in. It's such an important element. So look, we don't have any more questions just there. Oh, we've one popped up. So can you use an artificial light to attract flies?
Yeah, you can. We haven't found any artificial lights that that work as strongly as the sun. I don't know if right now. That was one of the first projects that I wanted to work on in my lab, and we just haven't gotten to it because I wanted to understand what intensity and what wavelength of light is optimal, or wavelengths of light would be optimal to really draw them out of the compost. But when I talk to the growers, at least here, sunlight is free, so they wouldn't have to pay for the electricity. They all have windows. And I was going to ask you the question, actually. So I know you grow in tunnels. Do those tunnels have any sources of natural light? Because really any source of natural light, if you can cover it with the electrostatic screening, could be used here. So artificial light, it's possible it just won't be as strong of an attractant, and you won't kill as many flies accordingly. I want to point out too that when the fly populations are low, the growers only had to apply maybe once a week, apply the pesticides, because it is a window and the pesticides can get knocked off by wind, or it is killing flies. But when the populations are really, really high, like what you saw in those 2 weeks, they were applying every day. The pesticide applications, because it's just applying a small amount of pesticide to one window, it takes less than a minute of time. So it's very quick.
Okay, just two quick questions before we end the session with yourself, Michael. So first one, quickly. So where can we get the screen, or who supplies it?
It's a company in California.
Maybe you might just later on after the webinar, maybe send me the details.
Yeah, I can do that. You can contact me. This number, 833-574-6743. That is the Mushroom Fly Hotline. Feel free to call it if you want to talk to me directly, or send me an email. Yeah, there's a company in California, as well as they're also selling it locally here now. But yeah, I can send you the email. I can send you the information, and we can make sure that they get it.
Okay.
It's called the name of the company is called Pollentec, Pollentec. It was originally invented to put on people's windows at home to filter out the pollen coming in.
Okay, perfect. Final question, Michael. Is there any viable biological control agent, fungal, bacterial, or viral, that could be used to control fly populations, making them to ineffect each other?
Oh, that's such a good question and a really good idea. We've spent a lot of time testing biological control agents. Nina Jenkins, another member of the mushroom fly team, her lab has looked extensively at biological control agents, and from what I understand, that they haven't found anything that worked. Not a larvicide, not on the adults. I have only been loosely connected to that research, but we haven't found anything fruitful yet.
Okay, perfect. Thanks a million, Michael. We're going to move on swiftly to, we've got Orla O'Halloran next. So Orla is a UCD Walsh Fellow student working with Teagasc on her project, which is adjusting the application timing of I can't pronounce that word, nematodes to improve fly mortality. Without further ado, I'll pass you over to Orla.
Thanks, Donal. Can you see my screen?
Yep.
Perfect. So good afternoon, everybody. Just as Donal mentioned there, I'm just going to report on our preliminary studies that we're working on to see can we adjust the application timing of entomopathogenic nematodes to improve sciarid mortality. So what I'm going to be reporting on today is based on different types of works that we've done. So some of them have included a grower survey, pest survey, field experiments, and laboratory experiments. So just a quick introduction to the project. The sciarid fly, like Orla ingenua, is known to be a significant vector of disease in the mushroom sector in Ireland. There hasn't been any recent surveys done of the fly population since Ireland's transition to phase 3 composting. So that was very important to get done to establish what the fly pest complex is at the moment. We also carried out a grower survey just to get an insight into what the growers, how they see what's happening on farms a lot, because they're there a lot more than we are. So from this, 58% of growers responded, indicating that they are very concerned about sciarid management. 37% of growers are concerned about pharid management. 91% of respondents indicated that sciarids or flies are the primary pest concerns, with 8% of those growers indicating that pharids are their primary pest concern. And from the growers' responses that we had, 83% of them actively monitor fly numbers on their farms. So the aim of the project is to establish through a pest survey what the pest complex population is within commercial tunnels. And from there, if like Orla ingenua is still the primary pest on farms, is to establish if the application timings of nematodes can be optimized to achieve a greater level of control. So for the survey that we performed on the pests, we have done this over 3 regionally separated hubs, each consisting of 3 commercial farms. From this, and as you can see from the image on the bottom right-hand corner, we divided the tunnel into grids, in which there were 6 traps in each grid. The grid remained in place for 3 weeks, and we replaced the traps in these grids every 7 days. The samples were then removed, and we identified the flies present taxonomically. A work that is currently in progress that we're not presenting today is that we're going to back up the taxonomic identification with the support of DNA barcoding. So from the initial results of the fly pest survey, we established that, like Orla ingenua, is the primary pest still present on commercial farms. Other species that we found to be present were from the Psychodidae family and the Sphaeroceridae family, as well as the pharid fly Megacelia halterata that was also present in small numbers. Just touching on something that we also observed while performing the pest survey was the fly catchments that we got. It also altered based on the integrity of the tunnels. So as you can see in the graph here, the tunnels that I have highlighted in orange, they all had these were the ones that had tunnels that they could have had rips or tears in the tunnels. Some of the examples you can see here on the right, and they all had a higher fly count than the tunnels here that were coming from commercial tunnels that didn't suffer any damage. So that is a factor into the quantity of flies present in tunnels. So I'm also touching on how growers reported on the efficacy of nematodes on their farms. 71% of the growers reported that the nematode efficacy was effective or extremely effective. 87% of respondents indicated that they hadn't noticed a decline in nematode efficacy, with 58% of growers responding that they are concerned, very concerned about cyard management. And again, the 37% indication the fires are their main concern. So we also asked the growers in the survey when they apply their nematodes, and from this 50% of respondents applied their nematodes on day 4 or day 5, and 25% applied before day 3. So what this says to us is the nematodes are being subjected to the first and second instars of the fly larvae. So the larvae develop in instars, which are kind of something like stages. So there's 4 stages in their development. And so if by applying at approximately between day 3 and day 5, they're being exposed to the first and second instar larvae. So we started performing sand bioassays to establish the efficacy of nematodes against each larval instar. Excuse me. So as you can see in the graph here, the second instar, there was a low mortality rate achieved, and then this increased with the later instar stages, was the third and the fourth instar. So from this, we're gathering that it's easier for the nematodes to be more effective when they're exposed to the later larval stages. So we've also done field trials using testing containers and with a high fly rate inside them here in Ashtown. So the results achieved showed a lot more variability in the results, but all nematode treatments displayed a lower yield of flies than that of the untreated control, which you can see here. But there is no statistically significant difference between the treatments. These are the initial results from the experiment. We need to repeat this experiment to see if the results are replicated, as well as needing to perform the same experiment under commercial tunnel conditions, just to establish whether the testing containers themselves might affect the nematode efficacy. So also what we also took a preliminary study on is the population sizes for each fly generation. So here you can see with the untreated control, the blue bar here is the F1 generation and the orange bars are the F2 generation. So the population size of cyards increases dramatically with each generation, so which shows us that it's very important to get a good control over the flies early on, so that to prevent each population size getting bigger and bigger. We also in this preliminary study did work using nematodes applied on day 2 and nematodes applied on day 4. So as you can see, this did have an effect on the population sizes for both. But as I said, this still is preliminary, so we are going to be continuing to work on this. Also, when we performed our field trials, we also analysed the viability of the nematodes throughout these field trials. Our field trials were focused primarily on the F1 generation, so we were only testing for the first 21 days of the nematodes applied. But we did find that the nematodes were viable up until day 21, taken at 3 testing points here. So we were able to establish that the nematodes are viable for these times, so they would be the good level of efficacy would be there for the larvae present in the casing. So taking from what we've learned, we looked at how the control would be working. So we looking at the day 4 application, and we can see from this that it is present through majority of the F1 cycle, and it is present for the 3rd and 4th instar of the F1 generations, where we expect that they will be the most they would have the best efficacy. But when you look further down here onto the F2 life cycle, the nematodes aren't present for the 3rd and 4th instars. So this would mean that they wouldn't give a good level of control from what we've learned already, currently have learned. They wouldn't be very efficacious against the F2 generation, so that which is of a larger generation, so it is putting a lot of pressure on them to be efficacious for the F1 generation. Whereas if you were to take a look over at an experimental nematode application, which we've done one test of that we are going to repeat a number of times, if you applied a later stage, the nematodes are still present for the late stages of the F1 generation, while also being present for the 3rd and 4th instars of the F2 generation. Now this, if we were to make this change, this would involve a lot of work, and also it would rely on the expertise of the growers, as it is close to the pinning stage. So the experimental nematode application that I'm currently testing is being applied on day 14, but this is quite close to the pinning stage. So there might have to be variety involved depending on the tunnel or on each individual farm that will record. It may require some changes to occur throughout the experiment plan. But as I said, this is just preliminary work. So we are going to be looking at this further, and we hope to be able to establish how close it is to the pinning stage, just to make sure that we don't cause any diseases such as bacterial blotch. So just in conclusion, the primary pest species within the commercial mushroom industry remains to be the Cyard fly, Lycoriella ingenua. The number of flies captured was influenced by the condition of the tunnel. Initial experimentation has showed that the nematodes are most effective against the later larval stages of Lycoriella ingenua. Nematode efficacy can be improved by altering the nematode application timing to coincide with the susceptibility of larvae instars, and adjustments to nematode application timings may optimize fly control as reduce the quantity of nematode applications required per crop cycle. Thank you very much for your attention. Sorry, Donal, you're on mute there.
Thanks a million for that, Orla. Yeah, so it's an interesting project that you're working on. Look, I'd be getting these questions all the time on the road. You know, are nematodes first of all working? There'd be a lot of growers that would be skeptical about it. But look, I think your research is answering that question. That yeah, they clearly are working and they're surviving the casing right through the day 21 there. I think you had on your slide. Yeah. So they are present, they're surviving. As long as they're applied correctly, obviously.
Yes. Yeah.
Perfect. So there's no questions just popping up at the moment, but Orla will maybe just hold you on the line. Actually, here's one coming through. So how long do you allow the nematodes to rehydrate before applying?
So we would give them, like we tend to follow the recommendations of the nematode brands, because we're also trying to establish what is going to be used in industry as well. So we do have to give them, we have to give them at least an hour to rehydrate, but we also test the nematodes before we apply them. So we would check them, we would take a sample size and put that under a microscope to make sure that they are, the vitality of the nematodes is optimum, just to make sure that what we are applying is sufficient to be, it is working. So we have the advantage of checking them under the microscope each time. So it can take from an hour to 2 hours on average from my experience.
And Orla, am I right in saying, like, just the perimeter from the data we've looked at already, are we looking at maybe the later to apply the nematodes, the better? As in, you know.
Yeah, I suppose, like, from the preliminary data that we do have, like a slightly later application could be better, in that just so the later instar stages seems to be when they're most susceptible, mainly because of their size. Like, the larvae of the cyards are incredibly small, and I can tell you that from trying to find them, but they're incredibly small. So it is the same issue that the nematodes have. So they often are trying to infect the larvae through the spiracles, which are very, very small air holes going down the larvae. So the larger the larva is, the larger the spiracles is, which makes it easier for the nematode to infect the larva. So the later that we can get to them, the better. So that's why it is looking at the 3rd and 4th instar are the best stages to be going for. But then we also have to take into account that it is applying this onto a crop. And that's where something I'm going to be looking at as well, to make sure that it's not being applied too close to pinning, so that we're not causing potentially bacterial blotch disease or something like that to be caused as well, because the mushrooms are also very important. So we're trying to find a way of just combining those two together. So I'm currently looking at approximately day 14, knowing that we might have to go back to maybe day 12, day 10, and the expertise of the grower applying them will come into a factor there, because they will be able to see themselves when the pinning is about to occur, and that's when they'll know when to apply the nematodes.
Yeah, that makes sense, Orla. Very practical stuff, you know. So another question, would you advise 2 applications? So one day 3, day 4, which growers would typically do, and the second application before or after first flush, or is this the second application a waste of time?
I suppose it's hard to know. It is kind of going to depend per farm. It kind of, I suppose what we're hoping with the later application stage is just that we could actually reduce it just down to 1 application. I know a lot of people do apply after first flush. It does depend on where the stage of the larvae are. I suppose when you're applying it into after first flush, again, you have to take into account what's going on in the casing, what stages of the larvae are you applying early on in the instar stages. I think you can kind of see it just back here. What's happening when you've coming into your first flush here. It could be early enough in the first or second instar of the F2 life cycle. So it might you could ultimately be like applying the day 3, day 4 nematodes at the very beginning of the crop. It could be applying them in the same methodology there, because again, it's still at the early instars. So it's something we can look at, but I suppose it'd be great if we could just get it all in one later application, and then there's an economic benefit to that as well, which would also be great.
Okay.
Can I just add in here, Donal, maybe that these sort of experiments are actually quite complicated to do, but I think the best way of getting answers to those questions is to do some trials where you're comparing the different treatments and trying to see what the resulting fly populations are. So I think that's what we would have to do to answer that question correctly. But as I say, these experiments are challenging to conduct. But yeah, we could do with those answers. I agree. Be good to know those answers.
Just as well say on that as well, Helen, when we're like something that, as you saw in the images there, we are using testing containers just so that we are able to contain the flies, and it's a very, very controlled environment. But that isn't we keep them under industry-like conditions. It's not exactly what's happening in the commercial tunnels. So that's why we're testing it in these testing containers first, and then we will move to test them under commercial conditions, just to make sure that it's right for both, because there is a small chance that there could be a bit difference there.
Great. Okay. And just a comment coming in here from Brendan. The problem I think what Brendan is saying is the problem is that we lose stagger if we water on before pinning. There's that risk that we will lose the stagger in the crop. So it's something obviously each grower is going to have to weigh up themselves whether to apply nematodes at that later stage. So appreciate that comment, Brendan. Grant. And we also just have a comment here on the chat function as well. Just a short note, mites are also working very well where existing CR problems exist on farms. This is previous work done by in the north in the early 2000s. They are widely available and they're used in glasshouse industry. So it's not really a new item, but it's effective when an issue is on a farm. Thanks for that. Okay, so we'll move on. Orla, thanks a million for your presentation. And if anyone wants to follow up with Orla after the presentation, contact myself, and we can help you as best we can. So we'll move on now to Helen. So everyone knows Helen has she's got a lifetime of experience working in mushroom research. So and her presentation is focused on tackling mushroom disease control in an environmentally conscious world. So Helen, take it away.
Okay, can you see that, everybody?
Perfect. Thanks, Helen.
Okay, afternoon, everybody. It's great to have such good attendance on such a lovely program of talks. A very interesting afternoon altogether. So I'm going to talk to you about tackling mushroom disease control in an environmentally conscious world. I think environmentally conscious has been a theme throughout this whole session, and it's something that is becoming more and more apparent for us as we go forward. We're all much more globally environmentally conscious as well. We hear about rising temperatures, climate change, and some of the key points to remember is that global average temperatures are rising at a phenomenal rate over the last 100 years. You can see the graph here on the left, that steep incline in global temperatures. We have to stop that at 1.5 degrees, certainly below 2 degrees, if we can, to prevent any major dramatic climate change events occurring. That rise in temperature is being driven by the burning of fossil fuels. And again, we can see in the graph on the right here how the burning of fossil fuels has also dramatically increased over the last 50 to 100 years. And so all of this activity is driving climate change, and this is resulting in adverse weather events across the globe, from polar ice caps melting to extensive drought occurring in areas, to flooding and fires and storms, as we've just had here in Ireland, 3 there in the last week. So we do need to be much more conscious of our activities that are contributing to this rise in global temperature. However, the environmental mushroom production has actually got quite good environmental credentials already. Positive aspects include the fact that we use agricultural waste streams. These are recycled like straw and manures. The spent substrate from the crop is returned to the land as a fertilizer. So we've got a circular economy process going there. Many of our growers would use alternative energy sources, such as solar power. Some will be wind power or wood chip boilers. And we also have relatively low pesticide use compared to other horticulture industries. But we do have to do more. We have to make sustainability front and center of all our activities going forward. And I think we're all very aware of that. It's being hammered home in the press all the time. So we need to be looking at more sustainable energy sources and green transport options, alternative packaging that's compostable or certainly plastic free if at all possible. Big element for us that we can actually do something positive about is integrated pest management, and I'm going to focus on that now in the rest of the talk. We've already heard about peat alternatives and casing. This is something we have to actively look to try and address in the very near future. And when we address all of these issues, what we will end up with is a sustainable and healthy food production system, maybe not quite like as we know it now, but it will certainly be more sustainable and will certainly have reduced carbon footprint. And these are objectives that all industries have to embrace going forward. So what I'd like to do today now is just to focus on integrated pest management of diseases. So just to remind us, integrated pest management emphasizes the growth of a healthy crop with the least possible disruption to the natural environment, and it encourages us to use natural pest control mechanisms. We've already heard from Michael, Wolfin there and Orla about natural pest control strategies being used for pest control. So the mushroom industry is already implementing integrated pest management, yet a lot of growers may not realize that. And what we have to do is get the growers to realize that a lot of what they're doing does fall into integrated pest management, and they need to be bringing this front and foremost in their documents to support their farms going forward, that they talk about their integrated pest management approach on their farms. So a group of scientists in Europe came up with 8 principles of integrated pest management for agriculture in general, but they're also very applicable to us in the mushroom sector and horticulture. And I'm going to go through these 8 principles and see how we implement them on mushroom farms. So the first principle is prevention. And again, our mushroom industry do a lot of prevention. So they are already implementing integrated pest management strategies. So prevention requires that you have good crop management, that you're using good quality substrates, your clean buildings and equipment. Nowadays, we have a lot of automated filling and casing, and this reduces the potential for contamination of crops and disease development. We would be hoping that all our growers have good hygiene levels. There's a lot of cleaning and disinfection and steam cookout going on. A lot of farms you visit are very, very clean. I'm always impressed when I visit farms late in the day to see how clean they can be because they've had a big wash down after the day's activities. And this is very important to try and prevent the buildup of contamination on a farm that leads to outbreaks of disease. The second aspect of prevention is the use of disease-resistant strains. Now, this is something that will be used in other areas of agriculture, perhaps, but unfortunately, we don't really have disease-resistant strains available to us in the mushroom sector as yet. However, there is a lot of research going on in this area. For example, at the Jilin University in China, Prof. Yu Li's group have identified a number of wild agaricus strains that have shown resistance to wet bubble disease, mycogony, and also to cobweb disease. So perhaps in the future we may see strains coming forward that have some resistance to these diseases. And there's a group of researchers in the Netherlands looking at cultivar resistance to bacterial blotch. So again, some of this information may feed into breeding programs. But just to mention that mushroom breeding is actually quite challenging because we also still want to have strains that are highly productive and of good quality. But hopefully into the future, we may see something emerging from this research. So that's prevention. Moving on to monitoring. Again, our industry would do a lot of monitoring of disease, and they mightn't think they're doing integrated pest management, but monitoring is a big part of that. And a key aspect of monitoring is that you have to be looking for your disease. So harvesters, it's important to educate harvesters to recognize and report any disease that they would see during their harvesting operations. It's a bit like a stitch in time saves 9. One piece of disease identified quickly and treated quickly will prevent a big outbreak of disease later on in a crop. If in doubt, get expert advice in terms of what you think. If there's something unusual happening, maybe you need to find out what the problem is. But overall, you need to be observing crops and recording disease levels on a daily basis. Growers need to know what the disease levels are. They need to know that nothing was seen, as opposed to we didn't really look for anything. And that those records then are going to help make the decisions on what to do next. And so the third principle then is the decision making based on those records of your disease or pest levels that you're recording. Do I treat or not treat? Or if I do treat, what do I treat and when do I treat? So if you're doing a good job and you've got clean crops, you don't need any intervention. But if you are picking up levels of disease, then you do have to do some intervention. And that intervention requires the application of treatments. And for integrated pest management, we're advised that we need to be considering the non-chemical methods first. And again, our industry will be doing a lot of that, because if you think about the spot treatment of disease when you observe it in a crop, that's a non-chemical treatment. But it must be done well and done carefully, because if that first piece of disease isn't spot treated carefully and taken out of circulation and gets watered over during between flushes, the result is a massive explosion of disease in the second and third flushes, a bit like the fly populations as well. So you have to identify and treat quickly in order to minimize the potential impact of diseases. Another potential option would be to stop after 2 flushes. So some organic growers would do this because generally the third flush would lead to more disease. So stopping after 2 flushes, you're reducing the impact of building up higher levels of disease. Stopping watering between flushes if disease levels are high, because again, this will reduce the impact of water dispersal and transmission of disease and explosions of disease in the next flush. Obviously, you have to manage people movement between houses so that you don't have people from older houses going into first flushes, and this will be something that will be done routinely on most farms. And also steam cookout is another non-chemical method where at the end of a crop we can kill off all the disease that was present in that house, and again eliminating the possibility of transmission. So a second non-chemical method for treatment are biological control agents. Now, there are a number of biological control agents available to us. For example, there's a number of bacillus-based products like Serenade, Serafil, and Amilo. And in the States, there's a product Zivion based on natamycin. We have Sporkill, which is based on long-chain fatty acids. But these commercial products, very often the efficacy data is scarce or weak. I just want to set these graphs over here on the right. So we did a little bit of work back in 2015 looking at some bacillus treatments for 3 diseases, wet bubble, dry bubble, and cobweb. And if we look at the top graph here and we see, let's just see if I got a pointer. Okay, so we see here, so when we have no treatment applied to the crop and we add dry bubble or wet bubble, we get a lot of disease being expressed. Here we have 3 treatments of bacillus, 1 dose, 2 doses or 3 doses, and we can see that it's taken 3 doses there to maybe have some impact on those disease levels, but it's still only about maybe 50% control. However, we must remember that these experiments are very often done with high spore loads, so high disease pressure, and maybe we have to reevaluate how we study the biocontrol agents to give them a better chance at having a significant effect. If we look at the work with the dry bubble, the Canicillium, again, in the absence of any fungicide treatment or bacillus treatment, we get lots of dry bubble developing. And when we apply our bacillus 1, 2, or 3 doses, we see here we're getting a significant reduction. So again, there's a suggestion of an impact, which is good. And again, if we remember, it's a high disease load. So again, if we try it at a lower disease level, maybe we might get better control. We have much less success with cobweb. Here you can see the levels of control are far less than in for the other 2 crops. Again, there's a lot of biological control research going on, but as Michael was saying, in terms of pest biological agents, not a lot is coming through that's showing high levels of efficacy, and this is a challenge to us going forward. But just to point out that the work is being done. Here's an example of where bacillus species are strongly inhibiting Trichoderma aggressivum. So that's a good thing. It's not in the crop situation, but we're seeing that there's a good reaction between the bacillus and the Trichoderma aggressivum. And when we look at what's happening within the Trichoderma, in the normal situation, when it's growing well, all these proteins and genes are active here. But when it's faced with the bacillus, we see they're all switched off. That's what the red means. Those growing genes are switched off. So something is happening quite dramatically within that organism. And what we need to try and do now is see, can we find anything among all of these processes that are going on in that interaction between the biocontrol agent and the pathogen that might give us a clue as to what a good biocontrol agent should have, and to try and see, can we take that forward into more effective products. So this is just a list of research that's going on at the moment with bacillus products. We've got antagonists and bacteriophages for Pseudomonas blotch organisms, and in research on potential biofungicides and other products that might have an impact on disease. But as Barsman, the scientists that came up with the 8 principles, were saying, maybe we also need to look at synergies between combining a number of different methods rather than one individually. One individually may give us a certain amount of control, but if we combine 2 or 3, maybe we get a better level of control. And no more than the peat research work, where we may have to accept something a little bit that's just okay as opposed to perfect. We may also have to accept some levels of disease as opposed to total disease control. So the 5th, 6th and 7th principles of integrated pest management focus on using chemicals. So once you've exhausted all the other options and you have a serious level of disease and you have to use a chemical, what do we do? Now for us, it's getting challenging because we don't have a lot of chemicals, but if we did, we have to try and choose the least toxic, because these are all chemicals that are dangerous for the environment and also for human health. And they can leave residues in food, so they have to be applied very carefully and by trained personnel. We need to minimize their use and only use them when needed, and to stave off the possibility of resistance emerging, we should alternate the products with different modes of actions. However, it is a challenge when you have so few products. For example, we've only got Sporgon and Vivando here in Ireland, and in the States they have Myrtect and Bravo. So you don't have too many products there to play with in terms of anti-resistance strategy. And then what happens if something does become resistant? So for example, here's a bit of work showing Vivando. So Vivando became available to us around about 2015. It was very effective against cobweb. Here we have explosions of cobweb when we have no treatment, but with Vivando and Sporgon, both of them are giving us very good control. However, as soon as 2018, there were reports that maybe Vivando was cobweb had become resistant to Vivando, and when we looked in the laboratory, we see, yes, that all these later isolates in red from 2019 onwards are all growing much better in the presence of high concentrations of Vivando than the control isolates here, all isolated before Vivando was used. And if we just look at a crop situation with those two different strains, one before Vivando use and one after Vivando use, we see both of them give good cobweb when the crop isn't treated with anything. When we treat the crops with Sporgon, we get good levels of control, but when we treat the crops with Vivando, we see only the earlier isolate is giving us cobweb control, and Vivando is not controlling the later isolate. So resistance to Vivando has definitely now been confirmed. So that product is less available to us now for cobweb control. And also just to mention that Sporgon, we're going to lose it next year when it has to be used up by June of 2023. So it's becoming very critical now in terms of how do we tackle our mushroom diseases. Which leads to the fact that what we have to do now, no more than with peat, we have to evaluate the processes that we're using and adopt a new approach in the light of reduced availability of chemicals. So we need to really up the ante in terms of our prevention and make sure we have good crop management and excellent hygiene procedures all of the time. We need to be monitoring for disease occurrences and keep records and know exactly what diseases are occurring and when, and deal with them as soon as possible. Make those decisions. Do you need to do any action, and focus on your non-chemical methods as early as possible to try and minimize disease spread. So we spot treat immediately. We reduce to 2 flushes if we have to, and we won't water between flushes. And all of this will help us to control that disease spread and transmission. We won't have much choice about selecting the least toxic chemical product because we don't have very many. We have little choice also at using anti-resistance approaches because again, if you don't have too many products, you can't alternate. And so really what we have to do now is to continue this process of knowing what we have, gather our knowledge, evaluate our crops, and take the earliest opportunities to try and control disease so that we have the least amount of disease developing later on. And all of this will eventually lead us to having a more environmentally conscious approach to disease control. So it's just a few resources there in terms of helping people to get on top of diseases, identifying them and what to do in terms of treating them. And then it just remains for me to thank everybody and acknowledge all the postgraduate students and researchers, colleagues and collaborators and funders who would have helped contribute to the research that I've spoken about today. Okay, thank you.
Thanks, Helen.
Okay.
And just see, don't have any questions coming in here at the minute. Just a comment on your presentation, Helen. Look, it's I'd be getting this again when I'm on the road. You know, growers would ask, you know, what is integrated pest management? What should I be putting down? What should I be putting down on my Board BIA audit form? You know, and they sort of think, is this extra work that I need to do? But in fact, it's not. It's no. Work that they're doing all the time.
Exactly.
That they're just not aware of. So it's. I suppose that was a nice summary, the way you put it there, Helen. That look, this is all you are doing.
Yeah, and I think we can maybe develop a little tool, an integrated pest management strategy for this farm, and just those 8 points. You know, they can write down what they're doing under those 8 points. I think everybody is doing something in that space. Yeah.
Yeah, absolutely. And to be honest, Helen, looking at other sectors, this would be one of the mushroom sector's strength, is that we are actually very good in this space.
Yeah.
And we probably don't get enough credit for it.
Exactly.
So look, it was great. It's good to highlight that point. Okay, so Helen, we'll keep you on the line. So if any questions come in for Helen, we can ask. So we'll just move on now to the next presentation. So we've got Joy Clark, who's going to give just a short update on her project. So Joy is a Walsh Scholar from Maynooth University. and she's now she's helping us out in Teagasc. So her project investigates the use of bacillus biocontrol agents as a treatment for mushroom diseases. So very much towards the topic that Helen had mentioned there. So it's Joy, you can hear me there now. So if you want to fire away.
Yeah, perfect. You can see my screen and hear me okay?
Yeah, perfect. Thank you.
Great. So hi, everyone. My name is Joy, and I'm a Walsh Scholar supported by Teagasc Mushroom University. And today I'm going to talk to you about the biological control of cobweb disease with bacillus. So cobweb disease is a very big problem for the mushroom industry worldwide. We know that it is caused by Cladobotrium species, and that cobweb disease can spread very quickly within a mushroom house. And this is because the spores from this pathogen are dry, they're very easily dispersed, and they can become airborne. So you can see in these images how quickly disease develops in an untreated plot. In terms of treatment options, we can solve patches of cobweb as they appear, which is seen here. Salting the patch will prevent the spread of the cobweb spores from that area, but it will also remove that area from production, and that may lead to issues with yield. Another option is to apply fungicides. So as Helen said, we can use prochloris manganese or Sporigon or metrophenone or Vivando. So from Helen's talk, we know there are a number of issues associated with the use of fungicides. They can be harmful to the environment and harmful to human health. And an over-reliance on select number of fungicides has resulted in pathogens which are now resistant to the treatment options. So for that reason, various governments and environmental agencies are now trying to promote integrated pest management or IPM strategies. And the number of fungicides which are approved for use on crops is beginning to diminish. So biological control agents are being investigated as a potential alternative for fungicide use. They're naturally occurring antagonists or competitors, and that means that we can find them naturally within the environment, whether it's the mushroom environment itself or elsewhere. And this makes them a more environmentally friendly option to apply to the crops than the chemical fungicides. Bacillus species in particular are commonly used as BCAs for the protection of a lot of plant crops. And this is because they have a number of different mechanisms for how they can control pathogens. Serenade is a commercially available biocontrol product. This has received approval for crops such as strawberries, raspberries, and tomatoes. It's generally used as a preventative treatment rather than a curative one. So for my research, I look at investigating bacillus BCAs, which can inhibit the growth of pathogens which cause disease to the white button mushroom. So I focus mainly on cobweb disease and dry bubble disease. And in the work I'm going to discuss today, I look at how a newly isolated BCA called Bacillus velizensis cos, which is isolated from a mushroom casing, can inhibit the pathogen which causes cobweb disease. So it's split into two areas. First, I look at how COS can inhibit Cladobotrium in the lab or in vitro. And then I look at inhibition in a field trial in vivo. And for this work, we included serenade and fungicide treatments as well. So I'm briefly going to go through the in vitro lab work because I think the field trial is a little bit more relevant today. But here I'm showing how the culture filtrate and the cells from the Bacillus COS can inhibit the growth of the Cladobotrium on plate cultures. We also grew the Cladobotrium in liquid flask cultures and then supplemented those flasks with culture filtrate from the Bacillus. And then after they had co-incubated together, we measured the weight of the Cladobotrium within each of the flasks. So the control flask, which had no culture filtrate, weighed 2.8 grams. And this was reduced down by 57% to 1.2 grams in the treatment flasks. Here are some images of some Cladobotrium hyphae, which were treated with culture filtrate from the Bacillus. And you'll notice how the treated hyphae appear irregular, they contain more globular structures, and they're just less healthy than what we're looking at for the control hyphae. We also did a lot of work characterizing the proteomic response of the Cladobotrium to the Bacillus culture filtrate. And what we found with this work was that the proteins that were statistically increased in the Cladobotrium samples treated with culture filtrate compared to the control were proteins that were involved with activities like proteolysis, DNA repair, and ubiquitination. And all of these are associated with a stress response. And then the proteins that had statistically decreased were involved in growth and translation. So overall, we've showed that yes, the culture filtrate from the Bacillus can inhibit the growth of the Cladobotrium in vitro, and that it is inducing an oxidative stress response from the pathogen. So then we moved on to our field trial where we investigated the inhibition of Cladobacterium from 4 different treatments. We had our Bacillus valizensis COS and Bacillus valizensis QST713, which is Serenade. And just to note, we applied the culture filtrate of the COS to our crops because we saw that that was effective in the in vitro work, but Serenade uses a cell suspension of Bacillus for its treatment. We also included 2 different fungicides, Sporogon and Vivando. For these 2 fungicides, we used 2 different strains of Cladobacterium that Helen had mentioned before. So the 1546 strain, which is a newly isolated strain, which has been shown to be resistant to metrophenone in the lab. And then the 618 strain, which is a much older isolate and has not been exposed to metrophenone. For the BCAs, so these 2 here, we just looked at the 1546 isolate. And our main idea was to look at the disease control efficacy of the 4 treatments. So here I'm showing the cobweb incidence at the end of the first flush of mushrooms. So we're measuring the area of cobweb disease within each treatment, and I've color coded here based on whether they were inoculated with 1546 in orange or 618 in purple. So if we begin to look at the treatments, Prochlorus manganese did a really good job of controlling cobweb disease at this point, especially compared to these control plots. The efficacy value for this treatment was calculated to be 90% for the 1546 strain and 97% for the 618 strain. For metrophenone, we have great control of 618 strain. There's a 99% efficacy, but you are seeing an increased level of cobweb in the 1546 plots. So the efficacy value is just 36% here. Serenade now had the highest level of cobweb disease amongst all the treatments with an efficacy value of 8%, whereas the COS BCA did a lot better with efficacy of 82% at this time. Then we took a second disease analysis at the end of the second flush of mushrooms. So just looking at the control plots here, you can see there is a big increase in the level of cobweb disease in the house from at this point, and therefore the efficacy values of the treatment have fallen, but they remain relatively high and statistically significant for Prochlorus manganese, 70% against 1546, and 72% against 1546 and 70% against 618. For metrophenone, still great control of the 618 strain with 96% efficacy, but you'll notice that the level of cobweb disease in the 1546 inoculated plots is actually higher than the control inoculated plots. And the same thing happens with Serenade. So neither of these treatments are actually effective right now. And then COS, there was an increased level of cobweb, especially compared to the first flush. The efficacy level is 30% now. So here are some representative plot images of the crop at the end of flush 2. So that would correlate with the second graph that I showed. And they're basically reflective of what we saw in that graph. The plots which have Prochlorus manganese and are inoculated with 1546 and 618 are remaining relatively free of disease, especially compared to these control plots here. For metrophenone, the 618 plots remaining clear, while the 1546 plot is heavily diseased. Then for our BCAs, Serenade up here, so we saw that this wasn't actually effective at this time point, and that's why we're seeing such heavily diseased crops and also areas where we had to salt the crop as well. And then for the COS, this one was a little bit more interesting because at the end of the first flush, the efficacy value was relatively good at 82%, but at this point it had reduced down to just 30%, which is why we're seeing disease. And we believe that this is because the level of cobweb disease had just risen too high at this point for the COS to be able to control. So for future trials, we're going to include lower inoculation rates, because we feel that these lower rates are actually more reflective of what the BCAs would come up against in a mushroom house. And therefore, we may get better efficacy values for the BCAs and ones that match the fungicides a little better. So from the trial, we have shown that the fungicides are still outcompeting the BCAs when it comes to protection against disease, especially at high disease levels. Prochlorus manganese performed the best out of all the treatments and was the most consistent against the 2 strains of Cladobacterium. The metrophenone then, or Vivando, worked really, really well against the Cladobacterium 618 strain, but failed to work against the 1546 strain. So this is because this strain is resistant to metrophenone, while the 618 strain is still sensitive. This highlights some of the issues that we have with fungicides in that they can be really effective for us and therefore we tend to rely on them. But once resistance does occur, they're not useful to us anymore. The COS, as I mentioned, had good efficacy when there is low levels of disease, but then it struggled to maintain that protection when disease levels got too high. And then for the Serenade, that one was a little bit more interesting because it didn't work at all against 1546, but there is some experimental trial data that shows it is somewhat effective against the pathogens of dry bubble and green mold disease. Not to the same extent as the fungicides, but maybe similar to how COS acted in our trial. So this is a result that we're going to continue to look into. So just in summary, I would say that it's unrealistic to believe that the fungicides are going to be replaced by the BCAs in the near future. But because of the problems we're having with resistance, we do need to start to think about how we can incorporate them into our treatment plans. So this may mean combining them with other IPM strategies like increased monitoring for disease and increased hygiene. And that could do enough to control cobweb disease at low levels in the house without having to implement in the fungicides, which would then reduce our reliance on fungicides and reduce the risks of resistance developing should we need to use them to prevent major crop losses. So thank you very much for everyone for listening.
Thanks very much, Joy. Excellent work, to be honest. It's very interesting seeing the difference between the fungicides versus the biological products.
Yeah.
Just one question I have. I don't know, maybe Helen, you might be able to help me out here. If you were to say the COS seems to be the most effective biological product, if you were to say if there was a farm who had high levels of cobweb, would applying fungicides and the COS together, would the fungicide have any effect on the biological product, or do we know?
I haven't actually thought about that yet. It's a very good question, because the BCAs, they're living organisms at the end of the day. So you don't want to apply anything that would impede their ability to prevent the pathogen in any way. So I guess it would be worth that. I'd love to do is to see their interaction together. Yeah.
I think it's something. Sometimes the chemicals are very specific in how they operate, so they'll have a very precise mode of action against fungi. So I would suspect that they may not have too much of an inhibition on the bacteria, but we'd have to evaluate that. Another thing just to point out here is that when growers have high levels of disease, it means they haven't been dealing with it soon enough. And really, that's the problem that has to be tackled, not what chemical can I apply. We really need to be getting growers to be looking at those crops intensively and identifying those first pieces of disease and treating them straight away so it doesn't get out of control. That's the challenge for growers now. Chemicals have been very good in helping not having to pay too much attention to that, because as we see, the spore gone has given great control for a long time, but still growers have lots of cobweb disease, and that's because even the spore gone can't cope with it when you're not dealing with it properly and you're allowing it to go everywhere. Like the fly populations, all of a sudden you've got billions of spores there. No chemical can deal with that. So we do have to get growers notching back and really paying attention to those first outbreaks of disease and treating them before there's a problem.
Yeah, no, I totally agree, Helen. It's always the best solution is to actually prevent the problem.
Yeah, and we have to get there because we're losing the chemicals. The pressure is on now because we're losing chemicals, and the biocontrols won't be as effective, but they might be able to help us, but we have to help ourselves as well.
I suppose the biocontrols will be built into maybe an integrated pest management plan going forward.
Yeah.
I think that's what we'll be looking at.
Yeah, as part of the monitoring and detecting and quick treatment, the biocontrols then will give you another little bit to help you get through that crop without too much problem, hopefully, going forward. Yeah,
great. Okay, we'll move on now to our final speaker. So last but not least, Laurent Hadvani. So Laurent has recently started with Teagasc, and his research project will focus on a new approach to biological control for dry bubble disease. So Laurent, I'll leave you to it, and if you'd share your screen for us.
Yes, thank you so much. Donal, can you hear me?
Yep, perfect.
Okay, super. Then I'm starting. So, dear colleagues, it's a pleasure for me to have the chance to present or introduce you our recently started project called La Cavir. The research aimed at the investigation into the potential role of fungal viruses in dry bubble disease with special focus on biological control is co-funded by Teagasc and the European Union. The total duration will be 3 years with 18 months to be spent at Okayama University, Japan, and the remaining part here at Teagasc.
Laurent, can you maybe go into presentation mode there?
Oh, yes, just a second. It should be.
We're still on the title. We're still on the title slide.
Really? Sorry.
Yeah.
Then...
So there's a green share screen icon on the bottom. Yeah, tick that.
Just a second. There was.
Yeah, just the presentation mode.
Yeah.
It just
and
needs
then
to go into...
now go into the presentation mode there, button on the bottom of your screen or wherever you
Is it okay?
No presentation mode.
It should be, just a second.
If you're maybe sharing a screen, that might be why.
Is it
just the little icon there just to the left of the zoom bar there at the bottom of your screen?
Yeah, that's it. So if you go now to display settings, Laurent, up the top.
Yes. Oh, yes.
And just swap screen. Yeah, click it.
Yes, and
yeah, that's it.
Okay,
yeah.
sorry for the confusion.
That's it.
Thank
that's
you.
Okay. Yeah.
The research aimed at the investigation of the potential role of fungal viruses in dry bubble disease is co-financed by Teagasc and the European Union for 3 years, with 18 months spent at Okayama University, Japan, and the remaining part at Teagasc. As for me, in my previous research, I've been engaged mainly in studying the mushroom green mold disease. And I would like to highlight just some of our findings. We reported the appearance of Trichoderma aggressivum, form aggressivum on the American biotype on button mushroom crops in Europe for the first time. This photo shows this particular case. It was taken at a mushroom farm in Hungary, where I'm from. And recently, we reported that further Trichoderma species also have the potential to cause green mold disease in the cultivation of different mushrooms. However, the main character of the current talk will be Lacanicillium fungicola, the causal agent of dry bubble disease. So Lacanicillium fungicola affects mainly button mushroom, but it has been reported from oyster mushroom cultivation as well. It has two varieties, fungicola, which causes disease in European countries, and Allophyllum, which is known from the American continent, Asia, and Australia. The fungus is a serious pest of button mushroom. It is a biotrophic pathogen, which means that it can grow inside the mushroom hyphae or mycelia. So far, no resistance of button mushroom to the pathogen has been detected, and the fungicide resistance of the fungus is also an issue. Therefore, the disease is difficult to control, which leads to a global problem with economic relevance. I'm switching to viruses now. They have always had a very bad public reputation, which is even more pronounced nowadays. Indeed, they can infect a wide range of living organisms, including bacteria, plants, animals, humans, and even fungi. The viruses of fungi are called mycoviruses, and although it may not be well known, they have been studied for a long time. Mycoviruses are mainly known from their negative side, as they can cause disease in the different symptoms in mushroom cultivation. For instance, there's a Lafrance disease, and mushroom virus X is also well known from the cultivation of button mushrooms. But mycoviruses are able to infect further mushrooms or macrofungi as well. So they are not restricted to button mushroom. However, mycoviruses may have positive sides as well. Several of them have already been reported to cause reduced virulence, so-called hypovirulence, in different plant pathogenic fungi, which means that the disease symptoms caused by the fungi can be substantially decreased. One of the most important examples is Cryphonectaria parasitica, the causal agent of the blight disease of sweet chestnut trees, which has been successfully controlled using certain mycoviruses. Further examples include Botrytis cinerea, which is a pathogen of soft fruits, such as strawberries or even grapes, Fusarium species, which are pathogens of cereals, and Sclerotinia sclerotium, which can infect a wide range of vegetable crops. On this picture, you can see the virus-free strain of this fungus in comparison with certain virus-infected isolates, and there are remarkable differences between the growth, so reduced growth, and also disease, reduced disease symptoms can be observed on rapeseed leaves in the case of the virus-infected strains. As I've mentioned, several mycoviruses are known to have the potential to cause reduced virulence in different plant pathogenic fungi. In addition, the reduced growth of virus-containing Mycogona perniciosa, the causal agent of wet bubble disease, has also been reported. Furthermore, recently, one of my former colleagues has detected mycoviruses in certain isolates of Lecanicilium fungicola as well. They are demonstrated here on the photo on the right, and you can see that different pattern was observed in the case of isolates originating from different countries, in this case Serbia and Ireland. And based on these facts, we have So based on these facts, we hypothesized that certain mycoviruses may also have the potential to control dry bubble disease. The objectives of the project are the examination of viruses in Lecanicilium fungicola, with special attention to those that may cause hypovirulence in the pathogen, and approaches for biological control or integrated pest management will also be taken. First, the viruses of Lecanicilium fungicola will be examined in the first phase of the project, and in the second part, their impact will be tested on Lecanicilium fungicola and button mushroom in cropping trials. We are going to scan a large set, more than 60 strains of Lecanicilium fungicola obtained from different countries, including Ireland, for the presence of mycoviruses. Then viruses will be eliminated from the carrier strains and isolated and introduced into virus-free isolates of Lecanicilium fungicola, as well as Agaricus bisporus. Then the effect of them will be tested on both Lecanicilium and Agaricus bisporus during or under the cultivation conditions. And we are also going to perform a detailed characterization on the interactions between Lecanicilium fungicola, virus-free and virus-containing isolates, and Agaricus bisporus under cultivation conditions. When we confronted Lecanicilium fungicola with Agaricus bisporus, well, you can see Agaricus on the left side of the photos, and then Lecanicilium on the right. A substantial or substantially different behavior was observed in the case of virus-free and virus-containing strains of the pathogen. You can see that the virus-free strain could overgrow the mushroom colony, whereas in the case of the virus-containing isolate, it seems to have stopped upon contact with the mushroom colony. So we consider this as a promising result. Currently, we are performing the molecular identification of Lacanthitilium fungicola strains at the variety level to distinguish between fungicola and Allophyllum. And you can see that the European isolates, including the Irish ones, belong to fungicola, while some Japanese isolates and those obtained from Australia represent Allophyllum. They can see at the bottom of this photo. And soon we are going on with fruit body infection assays as well. As a summary, I would like to say that during this project, we are going to examine the viruses in Lacanthitilium fungicola. It's going to be a fundamental research which is expected to provide deeper understanding of the pathology of dry bubble disease, but we are also going to focus on the potential of mycoviruses to control Lacanthitilium fungicola in mushroom crops. Finally, I would like to express my thanks to my colleagues. First of all, Dr. Helen Grogan, my primary supervisor, Mr. Brian McGuinness for the technical assistance, Professor Nobuhiro Suzuki as the supervisor for the outgoing phase, and of course for the financial support. And with this, I would like to thank you for your kind attention.
Thanks very much, Laurent. Very interesting project. You have a lot of work for you going forward. So look, it's interesting, yes. And you know, if you could come up with this groundbreaking strain that is resistant to disease, that would be unbelievable. So
yeah, I'll try to do my best.
Yeah. So great stuff.
I think
do you have any comments? Yeah.
I think it's important to say how, you know, we have to double our efforts in trying to find alternative ways of controlling disease, and this is one new approach. It's a novel approach. It's worked in some other host pathogen systems, and so we want to see, is there any possibility that we might be able to use that technology here in our mushroom crop. We have to keep looking at all possible sources of potential biocontrol agents, and this is an exciting and interesting and novel one. So I'm looking forward to this project, I have to say.
Good stuff.
A different aspect to viruses to what I've been working on all along.
Yeah, completely.
Yeah. Great stuff, Laurent. Thanks
you
very much for your presentation. And I'd just like to take this opportunity to thank all the speakers today. I think there were some excellent presentations, and I think there was a lot people could take away from it. So I hope you all found it interesting. I'd like to thank the audience, everyone who joined in, and for staying with us throughout this webinar. And like I said, this was aimed so all you could take something away from it, and I hope you did. So I think we'll wrap the webinar up there, and we'll hopefully see you again in the near future. So thanks, everybody.
Thank you so much.
Yeah, thanks, everybody.
Thanks.